Hello, welcome back. Now we're going to apply the procedure I taught you in the last set of notes to an actual example. The example I'm going to use is that of a motion estimator. As you most probably know, all video these days is recorded in a digital format. If we don't do some compression on that digital video, the files will become very large. Raw video works out to about 6 gigabits per second in terms of the bandwidth required. But the example you're watching right now, your typical downstream movie, your typical compressed video recorder on your cell phone, these are not at 6 gigabits per second, otherwise the files will be huge, the internet will be clogged, and you couldn't do all these things. So we need to compress it. There's several ways to compress digital video. They're actually quite effective. They can get good quality video well down to under 1 gigabit per second. One of the ways is to filter out the high frequency information. And you can actually see that as well on the screen in front of you. Another way is what is called a motion estimator. What this relies upon is that from frame to frame, not everything in the frame might actually change. So here's a simple example. One frame the cursor is here, next frame it's up there. A later frame it moves down there. And the rest of the screen hasn't changed. So rather than retransmit the entire screen, what we do is break it up into blocks, and by the way you can see these blocks on low quality video, and determine if the block is simply moved from frame to frame. So in the examples I just gave, several of the blocks on the right hand side are just simply moved from frame to frame. And rather than send the entire picture information, all we have to send is a motion vector. That is, this particular block has moved a certain number of pixels up and to the right. Of course, a pixel refers to a pixel element, essentially one dot on the screen. So let's say the digital video is captured 16 by 16 pixels in terms of the size of the blocks, which is fairly typical. Let's say this simplified example, we're looking at a 4 by 4 block. This is the reference block in frame 1 in the dotted line. What we do is search around the location of that reference block in frame 2 to see if it is just simply moved from one frame to the next. So in this particular example in frame 2, we can see that this original block of 4 pixels has moved 1 pixel to the right and 2 pixels up. Thus all we need to do is send a motion vector here being 1, 2, instead of sending the entire frame of data. And this greatly reduces the amount of data we transmit. And by the way, we actually will accept small changes in the details of the data and still say it's a suitable motion vector. For example, let's say this pixel was white in the second frame in this simple black and white example. We might still decide to accept that as a motion vector rather than resending the particular block with all the other steps, resending the particular block from scratch. Because the human eye is not terribly sensitive to these small changes. So we're going to apply a brute force algorithm to decide if we have good candidates in a frame of video, in 2 successive frames of video, for the motion vector. What we're going to do is take a smaller reference block from the first frame, search around it in a larger search window in frame 2, and look at every possible candidate for a motion vector. So for example, if this top left was a candidate, well, it is a candidate, we are going to evaluate it. That's the motion vector -3, 3. For each possible candidate, we'll calculate a distortion number, which in turn becomes a distortion vector across all the possible motion vectors. So the distortion number for the vector ij is given by this sum, where we compare the corresponding pixels in the reference frame with the corresponding pixels in the search frame. If the shifted pixel in the search frame is the same as the original pixel in the reference frame, this difference will be 0. And if that is true for all the pixels, then the sum of the differences will be 0. And we would have a perfect example for a motion vector, a perfect candidate for a motion vector. If this distortion number ends up being small, and how small depends on the algorithmic distinctions within your particular codec. If this reference vector number is small, you might still accept it as a motion vector, because the human eye is not terribly sensitive to small differences. So the idea is you calculate this distortion number for all the possible motion vectors. While doing that, you keep track of the best distortion to date and the associated motion vector. At the end of doing all these calculations, you look at your best candidate, decide if it's good enough or not, and if it is, just send that motion vector. So next, look at the system requirements that are part of the specification. I'm going to assume a 16 by 16 reference block, which is pretty typical from the standards. A 31 by 31 search window in the second frame. This is actually up to the designer and the algorithmic implementer. I'm going to assume that the 2 successive frames of video are stored in 2 read-ported memories. That is, I can do 2 reads simultaneously in each memory. To keep it simple, I'm going to have grayscale coded pixels, so I have to deal with the complexities of color. I'm going to use one particular standard in which there are 4096 reference blocks in a frame. I'm going to ease my requirements a bit by keeping the video rate kind of slow at 15 frames per second. And the system designer told me I have 2 clocks available, 130 and 260 megahertz. So the first thing we have to do is work out the system design. This is going to have both a bottom-up and a top-down element. The top-down element is working out what needs to be in the data path, because we're going to start with the data path, and how we're going to sequence operations in that data path in order to make the best use of our available hardware. However, here we need a bottom-up element as well. And the reason we need that is we have a hard real-time requirement. We have to meet the 15 frames per second requirement on the previous page. Thus, I need to know which system clock I can apply to this particular design. And to do that, I actually need to synthesize the adder accumulator, because that's my critical path. So in that adder accumulator, what we do is we take the difference between the pixel values in the 2 successive frames, take their modulus to keep that a positive number, and add that to the current value of the distortion vector, and store the result in the accumulator that's carrying the distortion vector. So we're doing 2 adds in the critical path as well as this modulus. And what I've said I've done here is I actually designed and synthesized just a small unit and found it could operate quite comfortably at 260 megahertz. I also know from my data sheets for my memories that they can also operate at this speed. So now I've done enough bottom-down design, I can start doing my top-down design. Next thing I have to do is work out my speeds and feeds. How I'm going to keep up with the hard real-time requirement in this design. So I have to calculate how many add accumulates I have to do per second, and thus how much hardware I need at the 260 megahertz clock rate. So this means doing some simple arithmetic. I have to process 4096 blocks at 15 frames per second. For each block, there are 256 motion vector candidates, as calculated here, and I've illustrated this calculation at the bottom here. So for example, I've got a 4x4 reference block looking in a larger 10x10 reference block. I look first at this possible candidate for motion vector, which is the -3 motion vector, then at this one, and so on. And it takes 7 searches to look at these 7 possible candidates. And I have to do that y direction 7 times in the x direction as I shift them over 1 pixel at a time. Thus it works out, for this smaller example, I need 49 possible candidates to search. So that's what I'm saying here. For the sizes, the reference frame and search window that I've chosen, there are 256 possible motion vectors, thus 256 searches that have to be done. For each search, we have to do 256 add accumulates. Multiply these together and we get 4 billion add accumulates per second. By the way, it would be very difficult to do this in software, even with today's fast CPUs, actually sustaining 4 billion add accumulates per second. And in fact, remember, each add accumulate is actually 2 adds, so it's actually 8 billion adds per second. Would be very difficult. That would take up all the cores in my CPU here, and it would only work if I could keep the adders 100% busy, which is actually unlikely given the overhead of instruction processing. So this is a classic example where you need an ASIC. You cannot do this fast enough in software. If you did an FPGA, it'd take up too much power and consume quite a bit of the FPGA. So where this is done is this is part of the CPU ASIC on your cell phone. There is a motion encoding unit on that. It takes up a few square millimeters, and it's done in a recent process, so we can fit it into a very small area of the silicon in your cell phone. This is a classic example also how Moore's law has led to increased capability in your mobile platforms. At 260, so we got this 4 billion add accumulates per second. So we need at least 16 of these adder accumulators at 260 megahertz in order to satisfy this throughput. Okay, so we're going to have 16 of these double add accumulators. We're now going to decide how to sequence the operations so as to keep these busy within the available memory bandwidth. So first of all, I'll try something simple. Remember, I've got 2 memories, one for each frame of video. They each have 2 read ports. I'm going to have 16 of these double add accumulators, and I'm going to do one motion vector calculation on each of these. Each of these calculations take 256 cycles. So I'm going to start my clock cycle 1 with doing the -8 calculation there, -8 -7 there, and so on. For each of these calculations, I can work out what particular operation I have to do each clock cycle. And that's what's listed here. Right. On the first accumulator, I've got to subtract, got to find the difference between R00 and S00. On the second accumulator, on the first cycle, between R00 and S01, and so on. So let's try this out. Let's see if this works. Well, if you look at this, you can see there's a problem. And what is that? I need 16 ports on my S memory, because each of these double adder accumulators is using a different entry in that S memory every clock cycle. Well, that's not going to work. I don't have the available memory bandwidth. So I've got to think of something else to do. So I look at this and I notice a pattern. That is the same as that. That is the same as that. If I rearrange the sequence of the operations a little, I will be able to reduce the number of ports required on the S memory. So here we try that in the next slide. All I do is for each accumulator left to right, I postpone starting the sequence of calculations by 1 clock cycle. This is a very small impact on my performance, because I'll go for billions of clock cycles before I start again. And it's solved my S memory problem. Here I just need S00 on clock cycle 1. Here I just need S01 on clock cycle 2, S02 on clock cycle 3, and so on. So does this work? Look at it. Yeah, all I did was move the problem. Look down here. I need R03, R02, R01, and R00. I just moved the problem to the R memory, so I haven't actually solved the problem. So I now just need a 16-port R memory instead. But notice something here. First cycle I read R00. Next cycle I read R01, and just reuse R00, and so on. So if I just keep R00 in the data path, I don't need to fetch it again. I can just keep it in the data path. In fact, all I need to do is shift it from here to here while fetching R01 in the first cycle. So I've got this pattern on these diagonals of these constant R terms. So R00, R01, and so on could be just shifted left to right in the data path to reduce the number of ports I need on the R memory. This is exactly what it's done on the next page. I've pipelined the output of the R memory. This is that pipeline there. And now I don't run out of memory ports. This sequence of operations works. I do actually need 2 memory ports on my S memory, because after at clock cycle 16 you start on a new row in that, and thus I need that. But this pipelining my R memory means I can still fit everything within the available bandwidth of the R memory. So the key here again was working out the sequence of micro operations, that is these guys, that have to happen on the data path that keeps my available hardware as busy as possible within the constraints of that hardware. Here the constraint was the memory bandwidth. Here I wanted to keep it at 16 double-added accumulators, and I've been able to do that through this clever addition of the R pipeline. And this is the type of thing, this is the creative art aspect of being a good hardware designer. So now I have my data path. And now that I've determined my sequence of operations and what's happening in there, I can sketch out the details of the data path. Notice, still no Verilog. I'm designing before coding. So what I have is an array of 16 PEs, or processing elements. Each of these consists of a mux to the S1 memory, because I will change which of these 2 ports I want to read. I also have my pipeline stage within the PE, though I haven't shown it here, and it will end up being within the PE. Within the PE, I have my difference calculator, which produces a positive number. On the first cycle of each add accumulate, that goes into the accumulator. On the next clock cycle, it's added to the current contents of the accumulator. So hence my accumulator, which is the only flip-flop I need, because that's the value I have to preserve between clock cycles, will have a mux on it, and the mux has 2 inputs, modulus A minus B for the first cycle, and add for the next 255 cycles. After 256 cycles, it will produce a distortion number, and the successive PEs over 16 cycles then will produce 1 distortion number each. By the way, you'll notice these muxes, these select lines for those will end up being control lines from my controller. I don't have to worry about that here. I can worry about that later. Remember, design the data path before designing the controller. Now we can start with coding. though I haven't actually finished my data path yet, I thought I'd show the code for the structure on the previous page. Here I have my R pipeline. Here I have my accumulator register. These are the only two registers I need because these are the only values that span clock cycles. Here's my S memory multiplexer with a control line S1, S2 mux, which will come from the controller eventually. Here's the combinational logic for the rest of this module. Because I found it useful to give names to signals within this logic, I did not put this in to the positive clock statement up there. Because then if I did that, everything assigned here would become the output of a flip-flop, and I don't want that. I only want these to be flip-flops. So the first thing I do here is my absolute subtraction. I want a positive number, I want that modulus. So I compare R with cell S and decide which to subtract from the other. This would not build two subtractors, it actually would build a mux and one add unit. I then do my addition on that, capturing the output carry as a separate logically named signal by using this concatenation here, which you've seen before. The reason I did that is because if this overflows, I don't want it to let it overflow. It has to stay saturated at FF if it overflows. Why is that? Because I'm interested in finding the smallest distortion number. I'd have two choices how to do that. I could build a much wider accumulator, so wide that it couldn't possibly overflow, but that's wasteful. If the distortion number is large, I really am not interested in how large it is. I'm only interested if it's small. So I thought, well, I'll keep the accumulator at only 8 bits and let it overflow. But if I let it overflow and roll back to 0, that distortion number will be small when it actually should be large. So what I do is detect the unsigned overflow, which you can just detect by looking at the carry flag. And if it overflows, I just keep the accumulate at FF, the largest number that can be stored within. So the idea is this difference accumulator will start at 0, keep counting up until it hits FF, and then it will stay at FF and for the rest of the calculation. FF is such a big number, this isn't a suitable candidate for a distortion vector. So I don't care how much bigger than FF it is, I'm just going to leave it at FF and then reject it later. I also have to implement that mux that's up that I had in there. That is at the start of every 256 clock cycles. I'm going to initialize accumulating with difference. There's no point initiating with 0, that's just wasting a clock cycle. This implements the mux, and you're seeing there, but, where's the else? You're going to have a latch. You screwed this up, Dr. Franzon. No, I haven't. Remember, it's not specifically whether there's an else or not. It just has to be that accumulate in has to be assigned for every possible way this code is executed. It's always assigned here. So these muxes just simply replace the value that's assigned there. I'm not building a mux. I don't have implied memory. So this is fine. And in fact, this has been verified and it works fine. I do need another part to my data path, and that is to keep track of my best current candidate for the motion vector and the associated best value for the distortion number. The way I do that is I connect my 16 PEs to this multiplexer. Every 256 cycles, I've got 16 cycles in which I want to read out the distortion numbers that are coming from these. I compare that distortion number with the best distortion to date, which obviously I have to initialize to some large value. If it's better than the best distortion to date, I put that in to this this register and keep that until it's overwritten with a better distortion number. At the same time, if it's the best distortion number to date, I have to get somewhere what the motion vector is that's associated with this and write this into a register that stores that motion vector. So the idea is 4 billion clock cycles later, I know the best possible motion vector. No, it's not 4 billion. Can't do that in my head. Whatever it is, whatever tens of millions clock cycles later, I have the best possible motion vector, and I have the best distortion associated with that. I decide if that distortion number is good enough in hardware that's not being illustrated here. If it is, I then have the motion vector stored there. So this completes the data path, but let's look at the coding of this particular unit. Here is that coding. When I start the calculation, I initialize the best distortion number to FF. The reason I do that is I want to make sure that I get some candidate for the motion vector. I'm surely going to have something better than FF. And more precisely, if I don't, then I'll just throw away the motion vector that's stored there. I'm not going to use it if it's FF. I have this unit down here that determines if I have a new best distortion number that is one that's better than the currently stored distortion number. If it is better, I'm going to overwrite the best distortion number register and the motion vector registers. This is that mux coming out from the array of PEs. I cannot pass arrays of vectors in my input and output ports, so I made this very wide PE out vector that concatenates all the PE outs together to create a much wider structure. So this mux selects what's 8 bits from that much wider structure. That selection is based on this PE ready signal, which is coming from my controller. Thus, what I've done is translated what's on this page into Verilog RTL, while considering all the details, including the constraints of the language. For example, that this could not be an array of vectors, so I had to work out a way to turn it into one longer vector. So now we've finished the data path, and we haven't yet worried about the controller. This is the beauty of separating control from data path. You can postpone thinking about the controller. You don't have to think it all at once, which gets more overwhelming. So the next step, step 3 here, is to identify the control points. And these are those. They're mostly the select lines for the muxes in the design. In addition, there's these vector numbers, which are the motion vectors being calculated. And in addition, there's the addresses that have to send to the memories. So this is a list of my control points. There's no status lines coming from my design. There's only control lines going into it. In quite a bit of detail. And you do want to do this at this level of detail. We next have to decide on the controller. And since what's going on here is we're simply sequencing through a large number of fixed calculations without any variation or any deviation, a controller can be basically based on a counter. We start counting at 1 and finish at, sorry, I don't remember the number, it's a very large number to mean that we finished doing this calculation. So my controller is a counter, since I have a linear sequence of steps with no branches in the equivalent finite state diagram. Turns out to be a 13-bit counter. When the external signal start is activated, here is active low, I start count at 13. until I complete it, and here I calculate if I completed, I just add 1 to count. This is my next state vector, which I'm just implementing as a counter. Then everything here is based on count. All I've done is work out how to calculate based on count when everything happens in this design, when all the control lines are activated, and also when I'm finished. So for example, this is combinational logic based on count to work out when each of the 16 PEs is ready. And here I've used a for loop to simplify the amount of coding I have to write. I just calculate so I iterate so this logic here for each of the PEs has a simple calculation to decide if that PE is ready or not. Down here I've got other simple calculations, or actually not so simple calculations, to work out the addresses, to work out when I need a new distortion number, because that's very closely related to PE ready, the control lines for the muxes, and so on. And the vectors for the current motion vector being calculated, which comes from subfields of count. I won't go through all the details here, but this is simply a decoder on the output of my counter to produce the values for the control lines going to my design that I previously identified, and basically thinking through this sequence of clock cycles 1 through to a very large number, and how to calculate on which clock cycle certain control lines are activated. So that's my controller. It's based on a counter. It's not simple to work out, but it's straightforward to work out. Just some notes on the design overall. As I said, the control strategy is a counter. I don't need reset because I can have start coming from something else that has reset sent to it, so they'll get me in the initial state. Though it might have been a good idea to apply reset to this counter. I have quite a hierarchy here. Here's my 3 leaf cell modules, 2 for the data path, 1 for the controller. The P is going to be replicated 16 times. I instance them in this design, top without memory, which is in turn instanced in top, which also has the memories in them. The reasons for this hierarchy are quite simple. These are the units I'm synthesizing. These units are not synthesized because I don't want to synthesize my memories. My memories are given to me by a memory designer. They're not synthesized, they're not made from standard cells. So these bottom 4 modules are collected together in one file and sent to the synthesis tool. They are integrated with top and the memories for use in the simulation, which is why I need this entire hierarchy, which in turn is instanced in a test fixture, which I've not shown. So this is the top. This is the synthesized part, the top without mem. Here are my declarations, which are mainly wires because of the outputs and modules. And here are those modules. I have 16 PEs and 1 comparator. And I've connected everything up using the dot convention, so the order doesn't matter precisely. Notice here I've selected out PE subfields for the wide PE vector that's an input to the comparator. I then have my controller down here. You can see why we use this dot convention. There's a lot of vectors, there's a lot of nets floating around here, and the dot convention makes it much easier to maintain this as you're debugging things and adding and deleting signals. Here's my top. I instance top without memory in it. Then I instance my 3 memories. And again, the outputs of all my modules are wires. So that brings us to the end of this particular submodule. I've given you a complete example of a relatively complex design, this motion estimator. I showed you how we designed the data path first by doing a combination of bottom-up exploration of how fast it can go, then top-down exploration of how much parallelism we needed to meet the real-time constraints, and how we're going to sequence the operations to use that parallelism within the available memory bandwidth. We sketched out this logic before capturing it as RTL. We then designed the controller, first of all determining the control points and the sequence in which they had to be toggled. Since there were no branches or decisions in that sequence, a counter was the best fit. So all we had to do was decode the count value to work out when the actual control lines could be toggled. I now encourage you to do the quiz associated with this submodule before going on to the next submodule. Thank you very much.